Welcome back. Let's now get into a very important topic of tensor data types. So we've briefly hinted on this before, and I said that let's create a tensor to begin with, float32 tensor, and we're going to go float32 tensor equals torch.tensor, and let's just put in the numbers 3, 6, 9. If you've ever played Need for Speed Underground, you'll know where 369 comes from. And then we're going to go dtype equals, let's just put none and see what happens, hey? Float32 tensor. Oh, what is the data type? Float32 tensor.dtype. Float32, even though we put none. This is because the default data type in PyTorch, even if it's specified as none, is going to come out as float32. What if we wanted to change that to something else? Well, let's type in here, float16. And now we've got float32 tensor. This variable name is a lie now because it's a float16 tensor. So we'll leave that as none. Let's go there. There's another parameter when creating tensors that's very important, which is device. So we'll see what that is later on. And then there's a final one, which is also very important, which is requires grad equals false. Now this could be true, of course. We're going to set this as false. So these are three of the most important parameters when you're creating tensors. Now, again, you won't necessarily always have to enter these when you're creating tensors because PyTorch does a lot of tensor creation behind the scenes for you. So let's just write out what these are. Data type is what, data type is the tensor, e.g. float32 or float16. Now, if you'd like to look at what data types are available for PyTorch tensors, we can go torch.tensor. And right up the top, unless the documentation changes, we have data types. It's so important that data types is the first thing that comes up when you're creating a tensor. So we have 32-bit floating point, 64-bit floating point, 16, 32-bit complex. Now, the most common ones that you will likely interact with are 32-bit floating point and 16-bit floating point. Now, what does this mean? What do these numbers actually mean? Well, they have to do with precision in computing. So let's look up that. Precision in computing. Precision, computer science. So in computer science, the precision of a numerical quantity, we're dealing with numbers, right, is a measure of the detail in which the quantity is expressed. This is usually measured in bits, but sometimes in decimal digits. It is related to precision in mathematics, which describes the number of digits that are used to express a value. So, for us, precision is the numerical quantity, is a measure of the detail, how much detail in which the quantity is expressed. So, I'm not going to dive into the background of computer science and how computers represent numbers. The important takeaway for you from this will be that single precision floating point is usually called float32. Which means, yeah, a number contains 32 bits in computer memory. So if you imagine, if we have a tensor that is using 32-bit floating point, the computer memory stores the number as 32 bits. Or if it has 16-bit floating point, it stores it as 16 bits, or 16 numbers representing, or 16, I'm not sure if a bit equates to a single number in computer memory. But what this means is that a 32-bit tensor is single precision. This is half precision. Now, this means that the default is 32, float32, torch.float32, as we've seen in code, which means it's going to take up a certain amount of space in computer memory. Now, you might be thinking, why would I do anything other than the default? Well, if you'd like to sacrifice some detail in how your number is represented, so instead of 32 bits, it's represented by 16 bits, you can calculate faster on numbers that take up less memory. So that is the main differentiator between 32-bit and 16-bit. But if you need more precision, you might go up to 64-bit. So just keep that in mind as you go forward. Single precision is 32, half precision is 16. What do these numbers represent? They represent how much detail a single number is stored in memory. That was a lot to take in. But we're talking about tensor data types. I'm spending a lot of time here because I'm going to put a note here. Note, tensor data types is one of the three big issues with PyTorch and deep learning. Or not issues, they're going to be errors that you run into in deep learning. Three big errors you'll run into with PyTorch and deep learning. So one is tensors not right data type. Two, tensors not right shape. We've seen a few shapes before. And three, tensors not on the right device. And so in this case, if we had a tensor that was float 16 and we were trying to do computations with a tensor that was float 32, we might run into some errors. And so that's the tensors not being in the right data type. So it's important to know about the D type parameter here. And then the tensors not being the right shape, well, that's once we get onto matrix multiplication, we'll see that if one tensor is a certain shape and another tensor is another shape, and those shapes don't line up, we're going to run into shape errors. And this is a perfect segue to the device. Device equals none. By default, this is going to be CPU. This is why we are using Google Colab, because it enables us to have access to, oh, we don't want to restart, enables us to have access to a GPU. As I've said before, a GPU enables us, so we could change this to CUDA. That would be, we'll see how to write device agnostic code later on. But this device, if you try to do operations between two tensors that are not on the same device, so for example, you have one tensor that lives on a GPU for fast computing, and you have another tensor that lives on a CPU, and you try to do something with them, well, PyTorch is going to throw you an error. And then finally, this last requires grad, is if you want PyTorch to track the gradients, we haven't covered what that is, of a tensor when it goes through certain numerical calculations. This is a bit of a bombardment, but I thought I'd throw these in as important parameters to be aware of since we're discussing data type. And really, it would be reminiscent of me to discuss data type without discussing not the right shape or not the right device. So, with that being said, let's write down here what device is your tensor on and whether or not to track gradients with this tensor's operations. So we have a float 32 tensor. Now, how might we change the tensor data type of this? Let's create float 16 tensor. And we saw that we could explicitly write in float 16 tensor, or we can just type in here float 16 tensor equals float 32 tensor dot type, and we're going to type in torch.float 16. Why float 16? Because, well, that's how we define float 16, or we could use half. So the same thing. These things are the same. Let's just do half. Or float 16 is more explicit for me. And then let's check out float 16 tensor. Beautiful. We've converted our float 32 tensor into float 16. So that is one of the ways that you'll be able to tackle the tensors not in the right data type issue that you run into. And just a little note on the precision in computing. If you'd like to read more on that, I'm going to link this in here. And this is all about how computers store numbers. So precision in computing. There we go. I'll just get rid of that. Wonderful. So give that a try, create some tensors, research, or go to the documentation of torch.tensor and see if you can find out a little bit more about D-type device and requires grad, and create some tensors of different data types. Play around with whatever the ones you want here and see if you can run into some errors. Maybe try to multiply two tensors together. So if you go float 16 tensor times float 32 tensor, give that a try and see what happens. I'll see you in the next video.